Hello everyone, my name is Clara Cuesta, and I'm glad to give an overview of supernova detection in neutrino experiments. Let's start with a brief introduction to supernova neutrinos. A core collapse supernova occurs when a massive star dies, and it is a huge source of neutrinos. Almost all the energy released is carried by the neutrinos, but are emitted in all flavors. However, detecting them is challenging. Because supernovae are rare events, we only expect 1 to 3 explosions per century in our galaxy, the neutrino emission lasts only about 10 seconds, and neutrinos are emitted in the long energy range, from 1 to 30 MeV. So experiments need to be optimized for this and cannot miss any day. Besides the neutrinos emitted in a single burst, it is possible to detect the background of neutrinos emitted by different supernovae in the history, which is called the diffuse supernova neutrino background. However, this signal is faint and has not been detected yet. With enough statistics, we can tell the story of the supernova looking at the neutrino emission. First, the core collapses and a shock wave is formed. At this infall moment, the medium is opaque even for neutrinos. The neutrino signal starts with a short, sharp neutronization burst, primarily composed of electron neutrinos. This quick and intense burst is followed by an accretion phase as matter falls onto the collapsed core. The later cooling phase, over 10 seconds, represents the main part of the signal, over which the protoneutron star sheds its trapped energy. So there's a lot of information about the supernova in this profile. To obtain it, you need the flavor content and the spectra of the neutrinos emitted that change through these phases. And the supernova evolution can be followed with a neutrino signal. Why do we want to detect supernova neutrinos? First, because we can learn a lot about the astrophysics of the core collapse. Neutrinos will bring information to confirm the explosion mechanism. The initial burst is primarily composed of electron neutrinos. But also, flavor transition effects can be observable in this burst. The formation of a black hole could cause a sharp cutoff of the neutrino flux. Shockwave effects could cause a time-dependent change in flavor and in the spectral composition as the shock wave propagates. The standard accretions and instabilities would give an oscillatory flavor-dependent modulation of the flux. Turbulence effects could also cause flavor-dependent spectral modification as a function of time. It will be especially of interest the observation of a supernova neutrino burst in coincidence with gravitational waves, which would also be prompt and could indeed provide a time reference for a time-of-flight analysis. And the supernova neutrino burst is prompt with respect to the electromagnetic supernova signal, and therefore can be exploited to provide an early warning to astronomers. Furthermore, in the worst case, a long-time scale-sensitive search without burst will also provide limits on the rate of core collapse supernova. Detecting neutrinos from a core collapse supernova, we can also learn about neutrinos themselves and particle physics. A core collapse supernova can be thought as an extremely hermetic system, which can be used to search for new physics like Goldstone bosons, neutrino magnetic moments, star photons, and particles, and extra-dimensional gauge bosons. A supernova burst is the only opportunity to study neutrino-neutrino interactions experimentally. But the coherent scattering of neutrinos of each other is very complex, as the neutrino density is very high and flavor transformations are not trivial. This is an active theoretical field, and the effects are not yet fully understood. It is possible to constrain the absolute neutrino mass and the mass ordering. The neutrino mass ordering affects the specific composition in multiple ways during the different eras of the neutrino mass. One of the most robust signatures is the early time signal, and the electron-neutrino component will be critical. This figure shows an example of the expected event rates as a function of time in the Dune experiment with 40 kilotons of liquid amnion. The event rate for the unrealistic case of no flavor transitions is shown in blue, and the event rate for the normal and inverted orderings are represented in red and green. Then, during the early stages of the event, the ordering can be identified. Have we ever detected supernova neutrinos? Yes, but only once. Back in 1987, about 25 neutrinos from a core collapse supernova were detected. The collapse occurred in the Large Magellanic Cloud, 51 kiloparsec away from the Earth. Over 168,000 years ago, It was discovered by Oscar Duhalde and Ian Shelton at Las Campanas Observatory in Chile. Ian was at the observatory but could appreciate the supernova with the naked eye. After the warning, neutrino experiments looked back at the data, and Kamiokande, IMB, and Maxan found an excess of events accounting for a total of 25 neutrino events. In this plot, we can see the event rate of the Kamiokande experiment, where the excess is clearly noticed. This observation confirmed the baseline model that was statistically limited, but opened the way to neutrino astronomy and to multi-messenger astronomy that is so important nowadays. The supernova neutrinos suffer different interactions when they encounter our detectors. First, the electron neutrinos or antineutrinos undergo charge current interaction with the nuclei. This is the most relevant interaction to capture the electron neutrinos that dominate the neutrinization phase. The neutral current interaction with nuclei for all types of neutrinos, although the cross-section for this interaction is lower. The elastic scattering on electrons or positrons, which is useful because the electron or positrons gives the information of the direction of the incoming neutrinos, which is useful for pointing towards the supernova. The antineutrinos undergo the inverse beta decay with protons, and the coherent elastic neutrino nucleus scattering, known as CEVENS, gives a low energy recoil. So the experiment needs to be as sensitive as possible to the different interactions, but it's also important that the nuclei use maximize the cross-section because they play an important role. What do we want for a supernova neutrino detector? Here is the wish list. The thresholds must be low, at least in the MeV range. We want the detector to be as big as possible. The bigger it is, the more events we will record, and we will be sensitive to supernovae farther away. We want to be sensitive to all neutrino flavors and distinguish among them. Good energy reconstruction and resolution, and event by event time resolution on the order of milliseconds. Good angular resolution for supernova pointing to locate the supernova. We want to have low radiological backgrounds and techniques to distinguish them from the supernova neutrinos. It's important to have a DAQ ready to trigger on the data and not miss the burst, and record a lot of information in a few seconds, which can be technically complicated. And it's not possible in the end to meet all these requirements with a single detector, but simultaneous observation by the combination of different experiments will be complementary. So the complementarity among the experiments is key. We can see this complementarity of the different detector technologies that are available nowadays. First, we have the water Cherenkov detectors like Super Kamiokande, Ice Cube, and Hyper Kamiokande. They are mostly sensitive to electron antineutrinos through inverse beta decay and to electron scattering, which gives pointing information. Their main advantage is the huge size of these detectors. Then we have the liquid scintillator detectors like Camlan, LVD, Nova, Borcino, Snow Plus, and Juno. They are also mostly sensitive to electron antineutrinos and to electron scattering. This is a robust technology. For instance, LVD has been running for more than 30 years in stable conditions. Then we have liquid argon detectors like Dune, SBND, Microboon, Dark Side, Argon. Then they have the unique sensitivity to electron neutrinos through the charge current interaction, and they are also sensitive to electric scattering, for instance. In these detectors, the size can be huge, and it's also good that they have good channel identification. The heavy nuclei experiments like HALO or ResNova are sensitive to electron neutrinos, but together with the full flux, they cannot distinguish. Their main advantage is that the heavy nuclei have a large cross-section that increases the sensitivity without needing this huge mass. Finally, there are other experiments devoted to dark matter or neutrino-less double beta decay searches that are sensitive to supernova neutrinos. I will briefly talk about some of these experiments, but if you want to find more information about them or the ones that I don't have time to talk about, you can check, for instance, the presentation at this conference that was very complete. Super Kamiokande is a water Cherenkov detector of 22.5 kilotons of fiducial volume. It is taking data since 2020 with gadolinium loading. Super K is mainly sensitive to electron antineutrinos, and for a 10 kiloparsec supernova, it could detect on the order of thousands of neutrinos. Could give information on pointing with a few degrees resolution, and has a supernova alert system sensitive farther away to the Large Magellanic Cloud, and an alert based on free supernova neutrinos that could alert even hours before the core collapse explosion. Super K has set up to date the most stringent limits on the diffuse supernova neutrino background. The next phase will be the Hyper Kamiokande experiment with a much larger volume of 188 kilotons. Hyper K is under construction and data taking is expected in 2027. It will be sensitive to the order of 10 to the 4 neutrinos for a 10 kiloparsec supernova, being 90% of them electron antineutrinos and 5% of them electron scattering events that will provide very good pointing capabilities. In general, the number of expected events depends on the supernova model, but and of course the distance to the supernova. So with enough statistics, we can distinguish between the different models. IceCube is the biggest water Cherenkov detector with 600 kiloton fiducial mass. However, it is only sensitive to electron antineutrinos and cannot reconstruct the event. For a 10 kiloparsec supernova, it could detect on the order of 10 to the 5 neutrinos. It is designed for high energy neutrinos and could be sensitive to post-explosion TeV neutrinos, assuming diffuse shock activation occurs. And it is foreseen an upgrade of the photon detectors that will increase the sensitivity to the supernova neutrino. An example of liquid scintillator experiment is Juno with 20 kiloton of fiducial volume. Juno is under construction. It can detect thousands of neutrinos for this 10 kiloparsec supernova that we use as an example, mainly electron antineutrinos, and also gives information on pointing. Juno will have good sensitivity to supernova neutrino background, and this plot shows the projected sensitivity of Juno compared to the best current limits. Dune is a huge liquid argon time projection chamber that will have 40 kilotons fiducial volume. It is under construction, and the first phase will start operating in 2029. Dune will record thousands of events for a 10 kiloparsec supernova. The main advantage is that most of them will be electron neutrinos, which dominate the first phase of the explosion. So this will provide valuable and unique information about the neutronization burst. An advantage of Dune is that it can reconstruct the tracks of the interaction, and it's sensitive to the electron scattering also. So it provides information on pointing with about few degrees of resolution. Finally, HALO is an example of heavy nuclei experiment running since 2012 with 79 tons of lead and helium neutron detectors. HALO sensitivity to charge current electron neutrino is also mixed with the sensitivity to all flavor neutrinos by a neutral current, and has not the availability to distinguish among them. But the advantage is the high cross-section that we can see in this plot, the large neutrino capture cross-section of lead. Here is a summary of the different running or proposed experiments showing their masses and the location and the expected number of events for a 10 kiloparsec supernova. And once more, the complementarity among them is the key point, that they have different strong points. So it's important, the coordination among the experiment, to ensure a prompt alert that is shared among them. With this aim, the supernova early warning system, SNEWS, was born more than 20 years ago. SNEWS is a global network of neutrino experiments sensitive to supernova neutrinos. The goal of SNEWS is to provide the astronomical community with a prompt alert of an immediate galactic core collapse event. Currently, there are 7 detectors sending alerts to the network: Kamiokande, LVD, KM3Net, IceCube, Camlan, Halo, and Nova. SNEWS 2.0 will have a larger network of neutrino detectors with more than 15 experiments simultaneously taking data. It is impossible to do inter-experiment triangulation based on their arrival time. And at this moment, the philosophy is that we don't need to avoid false positive at all costs, as it was foreseen at the beginning. What we want to prioritize is to start as much information as possible, so alerts can be set so that one fake positive per month is allowed. You can join the alert list if you want in this link and get an email if there's a warning. So to summarize, core collapse supernovae emit a huge source of neutrinos with unique information. Supernova neutrinos can provide information about fundamental processes related to the supernova physics and to the neutrino properties. There are theoretical models, but they need input from the experimental data. The diffuse supernova background neutrinos are possible to be detected in the next generation of neutrino experiments. There's a tremendous potential for detecting core collapse supernova neutrinos by present and future experiments. The complementarity among them maximizes the information we can obtain, and it is important to have a good detector response to reconstruct the neutrino flux evolution in time and the energy for the different neutrino flavors. And thank you very much for your attention.